Jensen, what's number 16? Back out because you put it away. You really expect me to believe that? You're correct, it is rotation. Sage, what is 17? Reflection, very good. If you remember, these were called transformations. Now, we did 3 transformations at the same time because these 3 transformations, translation, reflection, and rotation, none of them changed the shape. They may have turned it or twisted it, but none of them made it bigger or smaller. All the shapes were congruent. Well, what the last chapter we've been doing hasn't been about congruent. It's been about similarity, 2 shapes that are similar. Angles are the same, but the sides are proportional. Which is why today I'm going to show you the last kind of transformation, and it's called a dilation. Now, just like when you go to the doctor, and they dilate your eyes, to make your pupil bigger or smaller, that's all dilation is. This is an example. The red is the pre-image, the blue is the image of a dilation. Now, dilations are either enlargements or reductions. If it started with the red one and went to the blue one, which one would that be? An enlargement or a reduction? If it started here, it would be an enlargement. And if it went in the other direction, it would be a reduction. Very good. Now this goes in with the last chapter we did because when you dilate something, you're going to have a scale factor. How much bigger? How much smaller? So that's what we're going to be working on today. 6.7, dilation. Yes, we are, but not many. I think like 10 problems. Maybe 11. Not today. No worksheets today. You're welcome. 6.7. Your first piece of vocab. A dilation is a transformation that stretches or shrinks, which will actually be called an enlargement or a reduction. And every dilation has a center of dilation, although that's not really going to be a huge focus today. But nonetheless, it's important to know, every dilation has to be centered around something. Pretty much every dilation we do will be around the origin. .7 dilation. And if you're wondering, you don't have to write all that down, but if you're wondering why it's called a similarity transformation, that's because after you dilate something, it will be similar, which means the sides will be proportional and the angles will be the same. Who remembers what it means for sides to be proportional? Anybody? Sides proportional, what does that mean? Yes, sir. That's right. They all have to have the same scale factor. In fact, the very next slide is going to be talking about the scale factor of a dilation. And it's going to work just the same as all the other scale factors. You're going to have 2 shapes. You have to take one divided by the other. Boom, scale factor. I'll leave that up there. Who needs me to leave that up there? A tad longer, okay? Thank you. There will be 2 kinds of problems. That's a good question. One, it'll give you a pre-image and the scale factor, and you have to use that to come up with the image, which we're going to practice. And the other one, yeah, they'll give you 2 shapes, and you have to figure out the scale factor. They'll give you 2 of the 3 every time. Okay, the scale factor of a dilation is just going to work like the scale factor of any other similar shapes. Here's an example. Let's say here is a dilated thing. ABC, XYZ, and the image is ABC. Now, who remembers image? Is image the original or the after transformation piece? That's right. That's right. It was pre-image and image. So image of ABC means this one's the one they ended up with. So did it get smaller or bigger? It got smaller. It started with the red one, went to the blue one. If it ever gets smaller, that means your scale factor has to be less than 1. You know, if your scale factor is like 4, it's getting 4 times bigger. But if it's 1/4, it means it's getting 1/4 as big. So like here's an example. If this was like 8 and this was 2, just find any corresponding pieces. Doesn't even matter which ones they are. Would you agree that this piece and this piece correspond? I accidentally cut this off, but that'd be YZ and BC. So what would your scale factor be? Now slow down. Raise your hand if you think you can come to the scale factor, but I will warn you. Oh, okay. This is actually not right. Judging by what it says, this should actually be flipped. It'll always be your new picture over your old picture. It'll always be your image over your pre-image, therefore giving you a scale factor of 1/4. And you'll know you're right because it didn't get smaller or bigger. It got smaller, therefore that's less than 1. Your new will be on the bottom or top, and your old will be on the bottom. New over old. Spell no going down. Questions on that? Sure. So hopefully you can kind of see where this is going. You're going to have pictures today like that. And then you're going to have like a 4 and an X and a 2 and a Y or something. And you have to find the missing pieces by using the scale factor of dilation. Which is the same exact math we did last week. It just looks a little different. And it's called something different, but it's the same thing. You're just using scale factors to solve for the missing pieces on similar polygons. Again, we won't really worry about the center of dilation too much, although I actually set that up too. But every one we do today will be centered around the origin. You can probably see that because, you know, that's kind of the angle it's coming from. But we're not too worried about that right now. Okay? Alright. Here's an example. It says, draw a dilation of quadrilateral ABCD with the given vertices. Use a scale factor of 2 to draw your dilated image. In this case, LNNP. Now, does anybody have a theory about how we're going to use this scale factor, how we're going to apply that to all these vertices? Just a theory? It doesn't have to be right. You don't know. I mean, just very, very close. Actually, well, yes. First off, we drew ABCD right here, and you're actually one of those words you threw out was correct. All you have to do is multiply the scale factor by all of the coordinates, and that will give you your image, your dilated portion. Now, is this bigger or less than 1? Therefore, it was an enlargement or reduction. It was an enlargement. So we just take that and we multiply it by all the coordinates. 2 times 2, 2 times 1, 2 times 4, 2 times 1, 2 times 4, 2 times negative 1, 2 times 1, 2 times... We literally take that 2 and multiply it by every single piece. And then those are the coordinates to your dilated image. Sir. Like 2/5? Same thing. Now the multiplication might be a little harder just because if you don't like multiplying by fractions, but you're still going to do the same thing. 2/5 times this, 2/5 times this, 2/5 times this, etc. Good question. Most of them today will be pretty straightforward. You might have one of like 1/2, but they'll all be even. Stuff like that. We'll do some examples too. Question. Alright, first example we're going to do. Here are your coordinates. There's our scale factor, K. I don't know why they call it K, but they call it K. We have to graph it, and we have to find the images and graph of our image. Is this going to be an enlargement or reduction, Malik? What about you, Ariana? Enlargement or reduction? Madison? Somebody other than Donovan and Blake. Jensen, do you know why?
I know.
But you're right.
I know.
Trip, can you tell me why? How do we know this is going to be a reduction? That's right. The scale factor is less than 1. That's how you know if it's going to get bigger or smaller. If it's getting, this is telling you how much bigger it's going to get. It's going to get 1/5 as big, which means it's going to get smaller. So here we go. Let's plot this thing. I guess I really needed the whole left part of the axis since they're all positive numbers. So, we're really that piece either. First coordinate, 5, 0. 1, 2, 3, 4, 5. 5, 5. 1, 2, 3, 4, 5. And 10, 10. 6, 7, 8, 9, 10. 6, 7, 8, 9, 10. This isn't perfect, but it should look something like that. Oh, this one. I mean, not all of them. That just happened to be. It doesn't have to be a triangle. Now, we have to apply our scale factor. So let me put all my coordinates over here. Now, multiplying by a fraction isn't really as hard as people make it out to be. This is our pre-image. This will be our image, which I will do in red. Multiplying by a fraction, all you have to do is multiply by the numerator and divide by the denominator. So, we have to multiply all of these by 1/5. 5 times 1, 5. What's 5 divided by 5? 1. 0 times 1, 0 divided by 5, 0. There's our first coordinate. 5 times 1 is 5. 5 divided by 5 is 1 again. 5 times 1/5 will also be 1. What's 10 times 1/5? No. What's that? Very good. 2. And then 10 times 1/5 will be 2 again. You just multiply this by every single coordinate. And it will be a reduction, like we said. Sure, you could absolutely do that. Just multiply in your calculator. So that's, let's see, 1, 0, 1, 1, 2, 2, and you can see, there it is right out there. That is a 1/5 reduction. Okay, guys. That's nice. Okay. Questions about a step that we took? Great. Because I need you guys to try this one. Scale factor is 3. There's the coordinates. I'm going to come around and see what kind of progress you're making on this. I need you to graph it and find the new coordinates and then graph the image. You only have like 10 problems today in your homework, but you do have to graph. Yes. Most of the other ones are What's right of this? All right.
Is this enlargement or reduction? Three times.
Feeling pretty confident, though? Really confident?
I'm feeling really good. All I gotta do is you can sit right there and do it on the board. Hard as it looks. I already got some max. It's going to cover it above it. Just see here. Tap it. No, it's not. That's just a screen. I used to have one, and I used it to Are you? Sure. It's not pretty, but I think that's accurate. Hard to do. Why don't you get them the coordinates part of it? The multiplication of the coordinates. Yeah, right up. Yeah, well, they're already right here. So you just write the new coordinates. Oh, you're good at that. Look how nice those are. Now, how about this, Donovan? Switch colors to blue. Now, graph. That's right. Now, use your new coordinates to graph your bigger inflated balloon. No. Oh, no way, man. No, dude. That artwork is part of you now. Yeah. While he's drafting it, if you have questions, I can come right and answer them. Oh, yeah. That's why you lie. That's why it's helpful to do it on one axis that we can Hey, the dots are pretty good. Dum, 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 boom. Dum, 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 dum. Yeah, I always look at my computer, but you don't have an option on this.
You want me to really mess them up? Come on, Blake. Seriously. That'll work.
Yes. Okay. For all those watching out there, Blake cannot draw. Okay. All right, very good. Except for the horrible thing in the middle, which is my fault. Are there questions about where they got any of this?
I know, looks bad. Okay, well that's good, because those are the only two like that we're going to do. The only other examples we're going to do, here's one straight from your book. Find the scale factors of dilation used to define the missing pieces. Very good. What? Who can tell me how I'm going to find the scale factor of this thing?
Take a number from each one.
Now, before, actually, hold on one second. From the directions, read the directions and tell me, is this a reduction or an enlargement?
Read the directions, figure
It is, because it went from A to B, so from here to here, it's getting, which means our scale factor should be what? Should be bigger than 1, should be a number greater than 1. So, who can tell me with one of these what the scale factor is going to be and how you're going to get it? Cameron, was that your hand I saw? I think it was. Okay, Cameron, what's the side that you know of the red one? Well, let's start with this, the blue one. What's the side you know? So that you actually know. 3. Only one, right? So that's obviously the one we have to use. Which side corresponds with the 3 on the other triangle? Very good. Very good. Now, you know you're putting those two numbers together, so the only thing you don't know is it 3 over 6 or 6 over 3. Remember, you're going from A to B, so B has to be on top. Yes. 6 over 3, which reduces to what? You could reduce that if you wanted to, too. 2 over 1. Very good. So, now to find the rest of the pieces, who can tell me how to do that? Proportion. Sage. Yes, but I prefer if we just set it up as proportion. How would you set it up, Donovan? Ooh. 8 over m. Very good. If you go big to small, you have to keep going big to small. So it'll be 8 times 2m, or equals 2m. What will m be?
4.
4. So, now how am I going to solve for n? Same way. Now, yes, some of these you could be like, hey, they're just getting twice as big. So you could just divide the 10 by 2. I get that. But you couldn't do that if the scale factor wasn't so nice and neat as 2 over 1. If it was like 3/5, you would need to do your proportion. So let's go ahead and practice doing that. So 2 over 1 equals 10 over n. Cross multiply and solve, and you get n to be 5. Again, you'll really have to use a proportion when the scale factor is not so nice and neat. Questions? Well, today we're going to have double jeopardy.
What?
The first person to raise their hand and not just tell me the correct answer, but tell me why it's the correct answer, gets their assignment cut in half. You don't even have the question yet. But you have to tell me why. I'm not just taking answers. You don't even know what the answer is yet. No, put your hands down. Read it and tell me why the answer is what it is. Then I will accept your letter. This is a tricky question. That's why I gave it to you like this. That's what you're finding. If it was on there, you could just count it. That'd be easy. If you know how to get it, I will accept that as an answer. Yes, ma'am. But how will you find the coordinate? Can you tell me that?
I got
Well, that's close, but it's not as specific as I was going for. Clay, did you want to take it? You had your hand up next. Right. Well, actually, technically, since we're finding a point, it'd be 3/1. But that's very good. That's what I wanted. Therefore, what would H be? You're correct. Very good, sir. Clay, when I give everybody the assignment today, you can cut yours to just even. Right. He's exactly correct. Every dilation is either getting bigger or smaller by a scale factor. Now, I believe that's what Sage was getting to too, but he had the more complete answer. He said he knew every point had a perfect counterpoint. So, for instance, if you put F and Q together, Q is 1, 1, F is 3, 3. What's the scale factor from one coordinate to the other? What are we multiplying by? To get from here to here. 3. So he took his S coordinate, which is what corresponded with the H that we're looking for, multiplied that by 3. Well, S is 4, 5. Multiply that by 3, and you get 12, 15. C. That was a tricky question. So you can only do the even ones. Just mark on your paper that you got the bonus or something. All right, there you go. That's all for